Well, thank you very much for joining us today. Today we will be showing you some of the possibilities at your disposal when using two tools that we feel are the best in the market for architectural source code analysis and source code visualization and comprehension, LaTeX and Understand. Specifically, we're going to show and we're going to focus on how LaTeX enhances the information that you already get from Understand. So my name is Jason McAllister. I've been working now for Emenda for over 10 years. Also on the call is Sean Barrow and Neeraj Sangal from LaTeX. Sean is the Director of Sales and Marketing in LaTeX and has written articles on architectural refactoring, design rules, and architectural erosion. Neeraj is the Chief Technical Officer and founder of LaTeX. So without any further ado, thank you again all for coming. I will hand you over to the presenter rights to Sean, who will take the next part. So Sean, I'm going to give you presenter rights here.
Okay, excellent. Yeah, over there. Excellent, thank you, Jason. So I assume everyone can see my screen, say LaTeX Enterprise Suite, LaTeX Understand, and continuous architectural monitoring.
I can see that, yes.
Okay, excellent. So, as Jason said, what we're going to do today is we're going to make the assumption that you're already current Understand users, and we're going to just talk about how LaTeX can enhance the information that you're already getting from your Understand application, and just sort of what we can do in terms of architecture and architectural monitoring. That's sort of our focus, is the bigger picture. With Understand, you can really get a great understanding of or view of your code level information, and we really complement that, and that's what we're going to talk about today. So just a little bit about LaTeX. As Jason said, we've been around since 2004, and focusing on software architectural analysis tools, specifically LaTeX Architect. And the technology that we'll be talking about today, this DSM, or Dependency Structure Matrix technology, has its roots out of MIT here in the US, in Boston. And we're sold in 22 countries worldwide, obviously Germany and the European Union being one, some of those countries. You can see a kind of list of some of our biggest customers, a lot of these being European customers, Nokia, Ericsson, but we focus on those larger organizations that have large applications. So any of those types of companies, and C++ specifically, but we can also do I think 12 different languages right now. Java, C#, number of other languages like that. And today, what we're like I said, we're going to focus on how to import your Understand projects into LaTeX and get enhanced views of your applications. So like I was saying at the top, we kind of focus on the bigger picture in terms of your architecture and your applications, and with that we see kind of a focus on software maintainability. So a lot of the costs associated with software development is in the maintainability of that. And that's kind of where we try to focus, is reducing that software maintenance cost. And a lot of that software maintenance cost is trying to understand the software. So this may be an application that you worked on a year ago, 6 months ago, and it's hard to remember sort of everything you were doing at that time, especially if you've switched off on a different application. And we, if we can make a cleaner architecture, it's easier to have that understanding and hopefully reduce the software maintenance costs.
Can you change the microphone right under the drop down there?
Here?
Yeah.
Okay.
That should sound better.
Okay. Can everyone still hear me? We just switched microphones.
I can hear you fine.
Okay, excellent. Okay, so as I was saying, we try to help companies reduce their maintenance costs, and we see architecture as essential to that. A clean architecture, you can respond to changes faster, and if you can respond to new features and bug fixes faster, obviously the costs of those fixes and new features is going to be lower. A lot of times we'll get companies coming to us, when software velocity is slowing down, or costs for software maintenance are going up, and where we help is helping you clean up that architecture. Just a little bit about, as I was talking about, we really help companies enhance what their software are, their understand projects. So you're going to load in your software into understand, and we see ourselves as complementary to that. So we give you this, visualize the software, big picture view of what you see, and we'll show that to you in a technical demonstration today. We can help you define what your architecture is, or refactor it if you want to clean it up. So you can do a lot of what-if analysis on your architecture. What if I change these things? What if I remove these sort of dependencies? And then the last piece is we can help you control your software architecture going forward. You may clean it up, and then a developer could come in tomorrow and change things again. Every time someone touches the code, they could be adding bad dependencies. They could be adding cyclic dependencies, and we just help eliminate those sort of errors. And we'll be showing how to do that today. We also have some different metrics that Understand has, again, to enhance things. And some of those would be system cyclicality, system stability, and coupling, very architectural metrics. But we'll be showing a lot of that today. So just as an introduction to our technology, this is a typical view of what your architecture would look like. This is a UML diagram, specifically a class diagram. And for a small system, this is fine. You can see all of the relationships between classes and other relationships in the software. And at a small level, this is fine. The problem is when this becomes big. As you can see here on the right-hand side, this is a job application with 3,000 classes and 300 namespaces. And at a large level, it's just hard to understand sort of what's going on here. And that's why we skew towards larger organizations. They'll start having issues like what's on the right-hand side here. This is just, you can't really see a architectural pattern here or design pattern. So it's just hard to grasp sort of what's going on at a big level. And that's the problem is this type of diagrams just don't scale to large software applications. So what we came up with, or what specifically Neeraj came up with, is this concept of a dependency structure matrix for software. And it's just an easier way to understand your application. So this is a square matrix, and this can be your entire application. You can see all of the dependencies here, and you could do comprehensive architectural analysis on your application. So you can see all the modules here, and all the different dependencies, all of the possible bad dependencies and cycles, all in here. And when I turn things over to Neeraj, he's going to go into more detail on how to read this and what this means. But I just want to give you a quick introduction to what it can do. And as I said again at the top, is this supports multiple languages, obviously C, C++, Java, .NET, and a host of other languages for this application, to do this DSM analysis. And just one last slide on Lattice is where we fit into the typical development life cycle is so this is a desktop product similar to Understand. So you can load in your Understand projects into Lattice, and we'll be showing how to do that today. We also have a command line part of Lattice. So again, similar to Understand, that you can run each build, so you can, as you update the software, you can also run Lattice over that and get any violations to the architecture, what's changed, and new metrics. So you can kind of continuously monitor your architecture over time. We'll be showing a little bit of a demonstration to that as well. So with that, I'm going to turn things over to Niraj to do a more technical deep dive into LaTeX.
Thank you, Sean. So as Sean said, today's webinar, our focus is on LaTeX with Understand. So I'll start out with creating a LaTeX project from an Understand project. So that'll be the starting point, and we'll look at how to read a DSM, how to make sense of it, how to integrate it with continuous integration, and we'll end with talking about LaTeX Web, which is also a critical part of continuous integration. So let's get started, and I'll start with LaTeX Architect. So we'll start with the desktop product, LaTeX Architect, and then I'll show you start with using the GUI, but actually LaTeX has a very robust command line capabilities which allow you to do pretty much anything you do in the GUI, and so we'll show you that part of to do continuous integration with Understand with it, and then we'll go on to LaTeX Web. So let's simply select a new project to start the creation of a project. Well, we can choose a profile. If it is a C and C++, you can choose embedded, and this simply simplifies the menus that show up. I'll choose all. I'm very familiar with LaTeX, and so I don't need to simplify the menus, but and it'll also allow me to point to capabilities in LaTeX at the same time. So with this, we go on to the next, the dialog, part of the dialog, which is to create a new project. And I thought what we would do is to use an example that is part of, that comes with Understand. So we're using Understand for C++, and there is an example called fast grep. So it's a C and C++, a little example with C and C++ code base. And those of you, if you're familiar with Understand, I have a UDB file that I've already created from Understand. So the first step normally is to just let's start and give it the project a name. So we'll give it the same name. We'll call it fast grep. And then we choose a module type, and as you can see, this is already selected with Understand. But what Sean was referring to, there are many different ways of bringing information into LaTeX. It supports a number of different languages. For now, we'll focus on C and C++ using Understand. We'll select the UDB file, and now I've made that, and now I'm ready to create a project. A few comments regarding the Understand UDB file format. We support Understand 5.0, and we also support the versions prior to Understand 5.0. And there was a change in the format of UDB. So LaTeX comes built into the latest version of LaTeX is configured to run with the latest version of Understand. But if you have an older version of Understand, then you have to make a small switch inside the DLL that LaTeX uses, which is also part of the product, and the documentation explains that. All right, so now that I have selected the UDB file, I'm going to go ahead and create a project. And so LaTeX is using Understand's API to actually read that UDB file, and we have created a project. It's a small project, so it doesn't take any time at all. And we'll take a look at a dependency structure matrix for this project. So there it is. We have created a project, and now you can see, in fact, you can see that it's got these 9 files, which means that the matrix is 9 by 9. And you can actually look at, first, let's see how to read this. So you can see this arrow pointing down, and so you read this by going down the column. So this reads as egrep.c, which is a file depends on regular expression.c with a strength of 1. And if I go to the information pane, there are actually 3 different dependencies, and all 3 of them are method calls, so the invoke method call, and they are at these different line numbers. Or if I come in here, I can go and I can find, oh, there are many different dependencies, as you can see, at different line numbers that they happen to be located in. All right, so having done this, so this is how we read a DSM. You can also look in the usage pane when things get big, then the usage pane reflects that same information in the form of a hierarchy. So you can see that regular expression.c depends on regular expression.h, and that those dependencies include reference, include modify member, and so on. And at this point, LaTeX is showing you all the dependencies file by file. But just as in understand, LaTeX has loaded all of that information in, including down to what we call member level, which means that you can actually go down to the level of the method or the variables, the global variables that might exist. And all you need to do is what we call expand members. So I can simply select the entire project. It's a small project, so I just say expand members. And now everything is expanded, as you can see. And now, if I select a dependency, for instance, then I'm looking at that dependency which says that regular sub.c has two dependencies. One is a reference, which is an include dependency, and the other is a dependency on the regular expression class, or structure, and that it's a dependency on three different global data members, start P, program, and end P. So why do we do this? Why do we do member level for small projects? It's really simple. You can simply select it and keep it expanded all the time. But imagine that you had a project with 10,000 files or 20,000 files. Then it makes really sense for us to actually aggregate things up to a file level, but then select and collapse at individual cell level or individual file level, and be able to zoom in to any part of the information that you need. As a result, LaTeX scales exceptionally well, and we can load millions of lines of code into LaTeX simply because we are able to keep things in memory as appropriate. Of course, scalability is much more than just memory. It's also about being able to build things in parallel, for instance, or to be able to display things and so on. And LaTeX says, don't have time to go into all those details, but we've actually worked for many years and spent a lot of time working with customers being able to just do large scale systems really well. And when you're done, so as you can see, I can come in and I can simply say collapse, and I could actually go back to the way things were before. So really easy to be able to expand and collapse things. Now the next aspect that I wanted to touch, so we know how to read a DSM, and you see a bunch of dependencies. So what's interesting here? How should we look at this, or how should we visualize it in a way that allows us, that makes sense for us? And I'll show you what's called partitioning. And after that, we'll actually look at another visualization called a conceptual architecture diagram, a CAD diagram. So first, let's take a look at partitions. And partitioning helps us understand how things are organized. And you can choose a number of algorithms are available. For small systems, I often use proximity. Otherwise, for larger systems, component is good. And so I'll apply a component partitioner in this case, a proximity partitioner in this case. And notice that it split it up into 1, 2, 3, 4 different groups. And what's interesting about each of these groups is that the group below doesn't depend on the group above. And when you're looking at large systems, that very quickly maps into showing you what the layered structure of your system is. So you can see that these 3 set of files, egrep.c, timer.c, and try.c, those 3 of them, only have dependencies going downwards. So egrep.c depends on regular expression.c, strip break.c, and regular expression.h, and so on. All right. So, and you will find this very effective when you're loading large programs and be able to do that. And that's just the first aspect. If there were any cycles in here, it would actually identify the cycles for you as well. And you would see a cycle grouped together. And not only would you see it grouped together, it would actually highlight which dependencies to fix so that you can eliminate the cycle. And finally, the third part that it shows you is also that it groups things in a way that point out that these things belong at the same layer level, but they are independent subsystems. Again, pointing to a very common design pattern for our software, which is to build a common framework and build components on top of it. All right, so having done this very quickly, so we took a look at partitioning, which reordered this to actually reflect the architecture. And you can see how the header files, which is used by everybody, move to the bottom, how the application level stuff move to the top. And at the very top is a file which actually doesn't have any dependencies on any of these. All right, so having done this, let's just quickly take a look at a conceptual architecture diagram as well. All right, so we'll come in here. We will, we'll create a new view. So you can create as many DSMs or as many conceptual architecture diagrams, and conceptual architecture diagram is very simply done here. And you can see that it's actually already partitioned because it was the DSM was partitioned. And you can apply the same partitioning that you could do before. So if I want, I can undo that partitioning by applying alphabetical. So just list them out alphabetically. And if I select any subsystem, just like before, it's context sensitive. You see the dependencies associated with that particular file or subsystem, as we call it, if that was a directory and so on. Or you can select on any line, and those lines map to dependencies just as they used to before. So we can see all that. Now, having done this, I can also apply the same partitioning that I could earlier on. So I could come in here and apply, say, the same provider proximity partition, and I get this picture. And it's really easy to actually, there are some nice benefits to it. It's been built so you can very easily move things around. Let me create a little space here and move this sub file or subsystem right to the right of the selected box, to the right of egrep.c. And there it is. I've done that. And I want to get rid of this space. Just come in and you click on X, and there it is. I want to come in and I want to get rid of that space. That's easy too. Let's now fix this up. Let's just take this and okay. There. Okay, oh yeah, that's what I was doing. Let's just move this. Or even easier, make this smaller, click on the space and just distribute it out. There it is, and distribute it out. So very easily, actually, you can turn around and you can build these things. So you can drag boxes. And just like an editor would do, you also have the full undo and redo capabilities in DSM or in CAD or any of those. So let's just go back to a DSM for a second, and then let's create some rules as well. So let's come in and we can say that this is our layered structure. Let's assume that. So I simply come in here, and say create layering rules. And what does that do? That creates cells where dependencies are not allowed anymore. So that's it. That's all I wanted to do, and I've built a set of rules. You can actually select any individual cell, or if you wanted not to allow a dependency there, which says timer.c should not ever have dependencies on regular sub.c, I could come in here, modify a rule and say cannot use. And the moment I said this dependency is not allowed and there is a dependency, a violation appeared, as you can see. I'll undo that to remove that. And what this rule does is, and it's setting us up for continuous integration. So now that I've expressed my architectural intent that some dependencies are not allowed, if in future developers end up creating that dependency, then it'll be flagged as a violation. So very, very simply we'll do that. And in fact, let us add some dependencies into it. So let's come in and let's edit, let's go to the source of this file. And what I'm going to do now is I'm going to edit this file and introduce some dependencies. And let's add a dependency, include. A new include file is coming in. And this file doesn't even exist, by the way. And so this sort of, again, illustrates the robustness of understand. One of the strengths of understand is the ability to still parse and make sense of files that don't even compile. And that's oftentimes perfectly okay to do with understand, especially if you don't have a build system. It will actually still make sense of it. So we just introduced a dependency, and let me introduce yet another dependency. And I know that I'm going to create an external dependency to a symbol called tests. And that test symbol exists in one of the files. So there it is. I have added this dependency and I have saved it. So having saved this dependency, all right, so I've saved the dependency. Well, the DSM hasn't changed yet, but remember that we actually read the data from understands UDB file. And so we need to update the understands UDB file. And I could do it all using a GUI, but this is the part where I actually want to, or using the graphical user interface, I should be clear on it. Instead, we'll do it using command line capabilities. All right, so let us, well, we'll come back to LaTeX in a second. So let's start with a command prompt. So let's get rid of some of this so we can see. So let's start with a command prompt. So that's where we'll do things in command line. And for you to follow along, let me show you what I'm going to do to start with. So what do I need to do? And we're going to mimic what happens in your software development environment. Software developers have made a change. We made a change. We changed something. They have checked their change in. Now their change will go through the continuous integration of building it. So as part of your build process, you need to update the understand UDB file. And so what we need to do is to run understand in command line mode. And then once we have updated our UDB file, we will then update the LaTeX project, that too in command line mode. So first thing I'll do is I'll set the path so that for both understand and so we'll copy it and then we'll paste it. All right. So there it is. I can run this in command line mode. Now what I'll do is I will update the, oops, keeps doing that. Hold on. Let's get this out of the way here. And now let's run the understand command. So we'll do a copy and we'll paste that in here. So there it is. We're running understand in command line mode and we are updating the UDB file. So we are reanalyzing the source code, produced a bunch of warnings, no problems. Next, I'm going to having updated my database, understand database that was produced. I'm going to now run it in command line mode. And just to point out a few things in the command line mode, so there is a whole set of command line utilities that come with LaTeX. One of the most important ones is called LDC update, which takes the project that was created and updates it. And having updated the project, it then also creates an HTML file. And so let's just take a look at that HTML file. So there it is. We have created an HTML file, and notice it says atoms is LaTeX terminology for the domain element of C and C++. So it says no missing atoms. So we didn't remove any method. We didn't introduce a new file. We didn't take away a file or didn't do anything new. We simply made a change to regsub.c, and those changes took place, and it created a new dependency to timer.c on line 26. That was the extern that I added, where I changed a variable, and then I modified the global, and I also added that unresolved foo.h. So even though this file would lead to a compilation error, understand still picked it up, and then we've also found rule violations as we go along. So let's come in, and now let's update this project up, and that project has been updated. So let's close this project, and then we will update the project. So let's see. I think I forgot to save the rules. So anyway, we'll see it in a second. So let's open the project. And let's take a look at it. Oops. Yeah, I didn't save the project, and so that's what happened. Let's just create the same project, and you'll take a look at it in a second. Just now, hold on, and you will see what we did. So we can mimic. We can show you what the project looks like, and there it is. And now, if I apply partitioning here, you will see that we just introduced. Okay, we just introduced a new violation here, and since I forgot to save the rules, there was a rule here that I would have created, and that would have then showed up as a violation. But regardless, I'll show it to you in a second where we did create. So there was a bunch of rules that we created. That's the rule that because the file wasn't saved, didn't end up as a rule being created, and therefore was, now that we've created a rule, you can see that it's flagged as a violation. Regardless, so just to recapitulate what we did, we created a project, we made a set of rules associated with it, we organized the rules to reflect the design or the architecture. We then ran it in command line mode. We updated the UDB file. We then updated the project in LaTeX, and having done that, we then identified the rule violations. And I'll now take you to the next step, which is LaTeX also comes with what's called a LaTeX web, where you can actually publish these projects onto the repository. And there is a command line that's available for doing that as well. But let's just simply go to the LaTeX web, and so I can show you what it would look like. So there it is. That's LaTeX web. Oh, I have to log in. So I'll log into LaTeX web, and there it is. We can see that there is a project called FastGrep here, and it's actually red because there are actually violations in this project. So let's go in the project, and let's see that there are two snapshots actually here for the two projects. There are two snapshots, and there's a whole bunch of metrics and graphs and so on that have been produced. We could come in here, and we could, if we wanted to view the DSM, we could come in and actually take a look at the DSM and notice how that dependency from that we added became a violation because it violated the rules, and that's the global test data that we had changed. All right, so that's the first thing we did. That's the first thing to notice. Now let's take a look at the rest of the snapshot, rest of the database as well. Rest of the dashboard as well for this particular project. Every time you do a build, it actually produces delta information, and you can, and by default, it'll compare the last two snapshots. Of course, you can choose any snapshot to see, and you can choose to diff with any snapshot. So the ability to compare any two snapshots when you might have hundreds of snapshots exist. We're comparing 1.1 to 1.0, and you can see how the lines of code, we added 3 lines, and so those 3 lines are here. In fact, there's some cyclomatic complexity measurements, header file, and so on. This is the architecture metrics delta. So that was just, just the sheer counts and what changed. But you can actually see some critical metrics, and we'll take a look at more of those. You can see if any cycles were introduced, and you simply click on it, and you can see how we coupled timer.c and regsub.c are coupled when they were not supposed to be coupled. So sub.c regular, and this happens all the time. So this is a library which sits and provides services to application level stuff, and yet we have coupled the two together. And what that means, of course, is that now I have made it harder for me to test because when I make changes, those changes now ripple through much of the system. It's made it harder for me to understand because things are coupled to each other and so on. So all these things are well understood. And ultimately, they lead to a poor architecture, as has been shown repeatedly in lots of research lately, does lead to actually an increase in bugs that you will experience over time. So while your developers, all of us, are focused on fixing bugs, but architecture actually helps us reduce the number of bugs that will eventually be found, and makes things understandable. You can also see violations that were introduced. So simply clicking on the violations tells us that that's the place where we are modifying a global variable. That's where the dependency came in. And then some more deltas, such as what's new and what's changed. Some interesting things about the size of the files and so on. And then you can look at some of the graphs that I was talking about. And we'll take a look at examples of other graphs as well, but you can see how complexity increases. And it's very small system, but a small change which led to increased coupling actually reflects in a slight increase in complexity. So also does it lead to an increase in cyclicality. And so also does it lead to an increase in coupling and makes your system less stable. So you can see how coupling actually makes the metrics begin to reflect that. And since this was a small system, even a small change actually begins to show some of those things. And we can actually take a look at, and the fact that we have introduced a violation is also graphed for us. And now, if you want, we can actually take a look at some larger systems too. So let's take a medium-sized system like iso-aglib. So it's got like 400 or 500 different files, and you can see how complexity changes over time. And you can actually see how cyclicality is worsening, intercomponent cyclicality is worsening, and how stability is going down. And this is just, we're looking at just the last 5. If I were to look at the last 20, you would see big jumps actually, as coupling actually increasing pretty steadily over time, which is what happens to most software projects, which is that architecture erodes over time, and that's the standard path. And eventually, software erosion can reach a point where it becomes impossible to maintain. And as we fix bugs, as programmers, we are all trained to do that. We inadvertently are introducing new bugs, and this is an impact of what software erosion does to software projects over time. So with this, I'll end this demonstration, and just to recapitulate what we did, we looked at how we can load in and understand UDB file or the understand database into LaDix, and how we can then make it part of our continuous integration. We use LaDix to visualize, to express the architecture, to make rules. And then we use continuous integration to then automate the process so that we can prevent software architecture from eroding over time. So with this, I'll give it back to you, Sean.
Okay. Doris, thank you. So that's that's our demonstration today. I'm just going to leave you with this slide here. Oops. Let me just exit out of this. And so if you're if you're looking for more information on how we can help improve what you already get from Understand, we set up a website or a web page on our site. Lattice, SciTools, and SciTools Understand. It gives some more information on everything that we kind of talked about today. There's also the recording. And if you did want to try out Lattice, we do offer 15-day trials. You can get in touch with Jason at Emenda, and he can help you set up a trial. And you can check out the command line and the Lattice Architect and the web and the repo. So. With that, we're happy to take any questions on anything we presented today, or any other questions you might have on Lattice. So, does anyone have any questions on anything we presented today?
It looks like your presentation was so good that, and it was so clear that no one has any questions.
Hi, Sean. Thanks, Jason. I was busy shouting down the mic and had myself on mute. Sorry about that.
Yep.
Yeah, I had a question. Have you looked at? I know it didn't look like it was covered in the demo, but one thing that I know customers like from both Lattice and SciTools are the checkers that come with it. So as you are well aware, the Lattice has smart programs that helps to identify sort of architectural smells in your code. Now, I was just wondering whether there was any crossovers that was being worked with SciTools as well.
Great question. Nourish, you probably better.
Yeah. So as you know, SciTools provides a number of checkers for MISRA and so on. Lattice has an architectural focus, and we have a number of checkers. So, for instance, if you have dependencies where you inadvertently a base class ends up showing a dependency on a derived class, those checkers will catch it. Or, for instance, if you have include files or indirect includes which cause trouble, a number of those kinds of checkers actually come built into Lattice. And which actually one of our goals with that is that even if you didn't know the architecture, or if you're in the process of doing architecture analysis, but to actually get at those smells, then these are smart programs that you can run these checkers to be able to identify some key issues that you could fix right away.
That's right, and that also has command line ability as well to extract.
Actually, I don't. I have to verify that. That's actually tied into Lattice Web, so those checkers can actually be run from Lattice Web itself. So the moment you load a project into Lattice Web, you can just run the checker from there. The checker scripts are available. I just hesitate to say that. Normally, any script can be run from command line, but I in particular have not run those scripts. And my question is about the user interface, since they have an interactive user interface. Command line is probably not the best way to use those checkers, at least right now.
Okay, thank you.
And just to point out what the command line is, that obviously all the command line stuff that we showed today can be integrated with a Jenkins pipeline, run through a continuous integration with either Hudson, Jenkins, or if you use any of the other ones as well. So any other questions on LaTeX or how we work with Understand? Sounds like no. So Jason, I think we can wrap this up.
Yes, excellent. So Sean, Neeraj, thank you very, very much for that presentation. That was very interesting, and I'm sure those of our customers that use Understand have now a better understanding of what they can accomplish with LaTeX as well, using both tools. I will make this recording available so that we can send this out and people can grab this. But from my side here, thank you very much for the presentation, and thank you for everyone who joined us today. And yeah, I think we can end the meeting here.
Excellent.
Thank you.
Thank you, Sean. Thank you, Neeraj.
Okay. Thank you very much, guys. Bye-bye.
Thank you very much. Bye-bye.
Bye.
Yeah.